Okay, so this is going to be a 15 and 16 practice. We're going to look at some acids and base type problems similar to the ones you'll see on your test next week. And a lot of these questions are about things like finding the pH of a weak acid or a weak base or a buffer or a titration situation. And a lot of the challenge is just like the questions seem very similar when they're worded, but you kind of have to do different things for different problems. So I'm really going to spend my time kind of breaking down the wording, kind of show you my problem solving method I would use for each of these different 10 problems. I have this worksheet on Schoology if you would like to print it or work along with it, or you can just take notes or just watch, whatever you want to do. This isn't an assignment, but these questions, a couple of these might appear on your test. They might be verbatim from this practice. So I definitely recommend watching. So I'm just going to kind of get started, go through each of them. This first one, I have a bit of a typo thing, so just don't worry about what I scribbled out. But I'm just going to start reading it. 0.15 molar solution of weak acid. Okay, it doesn't tell me what acid it is, but it does tell me it's weak. So I like to use HA to represent a weak acid. And it tells me its pH. Okay, and I want to know what the pKa of this acid is. Okay, well, all weak acids will have a Ka, which is usually like some number 1 times 10 to the minus 5 or something. And I just want to know the pKa. So if I find the regular Ka, the pKa is relatively easy because the pKa is just the negative log of the Ka. So this problem is really about finding the Ka of my weak acid. All right, so how I would start a problem like this, I just have an acid. I'm not mixing it with anything. So I'm just going to start by writing how this acid will react. It's a weak acid, so I'm going to draw an equilibrium arrow. Acids, they'll lose an H+, and they'll be left with the conjugate base, which is A-. Now this is a weak acid equilibrium, so I need an ice table. And I'm going to plug in my information. I have the molarity of my weak acid. Plug that in here. And nothing on the problem tells me I have any H+ or A- also being added to my weak acid. All right, so this sort of problem, the basics here is I just have a weak acid splitting apart, and usually I do this problem to find its pH. This time pH is told to you. The alternative thing you can solve is the Ka. All right. So I'm just going to go ahead and fill out my ice table. That's a good place to start. I'm going to lose X. So I'll end up with 0.15 minus X. My hydrogen, I'm going to gain some amount X, and that'll be the same for my A-. So I have my equilibrium values, but I have this variable X, and I don't know what X is. All right. So I'm going to go ahead and write the other part of a normal ice table problem is writing your Ka, your products over reactants. So my two products are X and X at equilibrium. Divide by 0.15 minus X. Okay. Well, what I'm basically missing here is I need to solve this, and I need to know what X is to be able to solve that. And that's where the last bit of information is going to come into play. I know the pH at this situation, and pH gives you information about how much H+ you have. So off to the side, I'm going to write out my pH formula. pH is the negative log of H+, and I'm just going to plug in that pH in there. 2.51 negative log of H+. So if you have the pH of something, you can always find the amount of H+. Or if you have pOH, you can find the amount of OH-. Usually we would go backwards. Usually we would find H+ first and use that to find pH, but this way is totally valid too. I need to solve this for H+. So basically that means I need to get H+ by itself. I'm going to flip the negative over to the other side by multiplying each side by -1. I want to do the inverse operation of the log, which is the exponential 10 to the power of. The left side, I have 10 to the negative 2.51, 10 to the log. Those will cancel, and I'm just left with H+. Plug this other bit into my calculator. Brought a real calculator today. And I get my decimal. And that is how much H+ I have at equilibrium. That's what my pH tells me, is how much H+ I have. This is this value, the amount of H+ at equilibrium. In other words, This is just x. So I'm going to take this number, plug it in for x, x, and x, and that'll help me solve Ka. So 0.00309, 0.00309. Now this part, we usually get rid of the minus x, which you totally can, but since we have the actual number, technically it's slightly more accurate to do this, but either way it'll be fine. All right, so I'm going to plug in everything I know. Take 0.00309 times 0.00309, divide by 0.15 minus 0.00309, and I get 6.5 times 10 to the negative 5 as my Ka. Right? And that's usually where you have to stop, but I even added one more step. I want the pKa. So to get the pKa, P means take the negative log. So I'm just going to take the negative log of my answer. Negative log of my answer is, answer 4.19. And that is the pKa of that acid. pKa and Ka are just like H plus and pH. It's just a different way to look at a Ka. For an acid, the bigger this number is, its Ka, the stronger it is, because that means more of it turns into products. And the pKa is just like pH, where actually the lower the pKa is, the stronger the acid is. Because if it's a negative logarithm, it flips the scale upside down. Okay, next question, number 2. I want to calculate the pH of 0.002 molar solution of perchloric acid. Okay, so again, I just have an acid. I'm going to start with just one thing. We're not mixing anything yet, because that complicates it. But I have perchloric acid, HCl of 4. Hopefully you recognize that is a strong acid. The other way you could recognize it is this problem would be impossible to solve because it doesn't give you a Ka. Right? And that's because strong acids don't have a Ka. That's why it doesn't have to give you one. So that's kind of a hint. If you couldn't remember this was a strong acid, like, okay, it doesn't give me a Ka, so I'm going to play the odds. That's a strong acid. I want to find the pH of a strong acid. That's so much easier. You can just use the pH formula. This strong acid, if you want to write the reaction, I'll write it out just to practice. You write it with a right-facing arrow because this is strong. And strong acids lose all of their protons, 100% dissociation. And there's 0% of the reaction going backwards. So everything's going to the right, nothing's going to the left. And that just means if I start with 0.002 molar of this, I'm going to make 0.002 molar of H+. So I really can just take this number and plug it into the pH formula. That's why it's important to know your strong acids and bases, because there will be problems on your test that are as simple as this. 2.70 is my answer. Number 3 is related. I want to calculate the pH of, here's my strength, solution of strontium hydroxide, which is a strong base. Okay, so it's essentially the same thing. If I write the reaction of this strong base, 100% of this will just turn into its products. You'll have some strontium 2+ and OH-. Bases lose their OHs. Since there's a 2 here, you actually lose 2 OHs every time. Just make sure you have the 2 in front here. Okay. Half of the strong bases are this way. They have a 2 hydroxide groups, and they will make 2 every time they dissociate. So just be careful about that if you see a 2 here. Technically, the strong acids, one of them, sulfuric acid, has a 2, and it's kind of complicated how the chemistry works with it. But just be careful, especially with the bases here. All right, so I have 0.00345 of this, but my OH has a 2 in front, so I actually make twice as much of that. So I'm going to take my number, 0.00345 times 2, and I get 0.0069 OH minus. That's my hydroxide concentration, which I cannot plug into the pH formula. I can plug into the pOH formula. That's a very common mistake that I notice is make sure if you have OH, you use the pOH formula. A lot of people will skip that step and try to use the pH formula. Okay, that's my concentration. Now just take the negative log of it. 2.16. That's my pOH. So if you want to find the pH, just do 14 minus whatever you get. Which I get 11.84 as my pH. Okay, so 2 and 3 are strong acids, strong bases. You don't have to do ice tables. You don't really have to do much stoichiometry. I chose to write the reactions. You wouldn't really have to, especially for something like HClO4, because these numbers are just the same. You wouldn't even have to write this reaction unless you're like specifically asked to. You can kind of recognize, since it's OH2, I'm just going to double this number. Okay, next question. Acetic acid. Okay, so when I see acetic acid, I'm thinking, I know this is a weak acid. It's probably the most common weak acid we use. And it immediately tells me it's Ka, so that just kind of verifies for me. Yep, it is definitely a weak acid. Okay. What is the pH of a buffer? Okay, so I see buffer pH. What I'm thinking is I'm probably going to need the Henderson-Hasselbalch equation. Oops. pKa plus the log of A minus over HA concentration. That's what I'm doing in my head. I don't even know if I need it yet, but when I see buffers and pH, that's immediately what comes to mind. Okay. The other thing that comes to mind with buffers is you need a weak acid and its conjugate base. I already have the weak acid, so I'm expecting the conjugate base, have some information about that as we go. The alternative would be you could have just a base, like a weak base, and its conjugate acid. Like either of those are both buffers. They work the same. Okay, so that's kind of what I'm thinking when I'm reading this. And then I get it's made from 0.150 molar acid, has an H in front, so I know this is my weak acid, and 0.530 molar C2H3O2 is our base. It has a minus, and it doesn't have the H in the front because it lost an H plus when it reacts, so this is my A minus. Okay, so I am just going to use this Henderson-Hasselbalch equation. I have pretty much everything I need. I'm looking for pH. Ka, I have, that was given to me. The log, I need the concentration of A minus, which is right here. I have molarity of my base. And concentration of HA, I have molarity of my acid. So I'm just going to plug all of that stuff in. Okay, write my formula. pH equals negative log Ka is 1.8 times 10 to the minus 5 plus the log of my base concentration is the 0.53. My acid concentration is 0.150. I'm just going to break this into the two little parts. I have first the negative log of 1.8 times 10 to the negative 5. I get 4.74 for that first term. Plus the log, and I'm just going to type 0.53 divided by 0.15 of 0.548. And now I just add those numbers together. I get 5.29 as my final pH. Okay, that number makes sense to me. This over here, 4.74, that's my pH when I have the exact same amount of acid and base. So if these numbers are identical, the pH and pK will be the same. But in this case, I have more, this number is bigger, I have more base than I do acid. And that just means my pH should go up, because adding a base, having more base than acid, will make your pH increase. So I always like to check my work at the end of a Henderson-Hasselbalch equation to make sure I didn't flip these numbers or something. You might have noticed this was significantly less work than some of the problems we do with buffers. And that is because this problem just gives you molarity straight up, and it doesn't give you information about milliliters or adding these two things together. So when you get a problem like this, what that means is you have one solution, right? One solution with one volume, right? That volume is not changing. And inside this liquid, I have both of these things. I have 0.150 molar of my acid floating around in there, and I have 0.530 molar of my base floating around in there, right? So it's already all in the same solution. So I can just use my molarities without having to worry about converting to moles or anything like that. This is probably the more typical type of buffer problem you'll have to solve realistically, right? It's a little bit nicer. Now, the reason we have to break it into two different tables sometimes and it gets more complicated is that basically I give you this exact same question, but it would be phrased just a little bit different. It would say I'm going to add like 100 milliliters of 0.150 molar acetic acid to, like, I don't know, whatever, 200 milliliters of 0.1 molar base. I'll just write A- to shorten it. Okay. This problem is more work because you're changing the volume in the problem. You're adding two different solutions together. The way this is worded, it just implies you have one solution, the volume stays the same, it's not going to affect any of your math. So we're going to do some questions later, next, that's slightly different, and we're going to essentially do the same math, but we have to add some extra steps to account for the fact that we're adding two different liquids together. Adding liquids dilutes each other, right? I'm increasing my total volume, which will actually change these concentrations. So let's take a look at that. So what is the pH of a solution? So I'm looking for pH again. Composed of 500 milliliters of 0.250 molar sodium hydroxide. Okay, so at 500 milliliters, 0.25 molar sodium hydroxide, that is a strong base. So I have some amount of moles of strong base. I know the volume, I know the polarity. And 400 milliliters of 0.2 molar hydrochloric acid. Hey, that's a strong acid. Both these things are strong, so there's not going to be a buffer solution at all, right? I only use buffers when I have a weak acid or weak base, or a weak acid and its conjugate base, or vice versa. Strong acid, strong base, I'm mixing an acid and base together. So in this case, that's kind of what I'm thinking ahead of time. Eventually, I'm going to solve pH just using our normal pH formula. Right? I'm not going to have to use the Henderson-Hasselbalch for sure. The other thing that's different about this problem is I'm taking an acid and base and adding them together. So whenever that happens, you definitely want to start by writing out that reaction. My HCl and my NaOH reacting together, acids and base will neutralize each other, which always proceeds fully to your products. AH and OH will make H2O. The Na and Cl will make NaCl. Okay? Because both these things are strong, this is a strong acid, this is a strong base, the products are pretty much irrelevant. Okay? If one of these things were weak, if I had a weak acid or a weak base, then this salt would be relevant. And the reason it would be relevant is because you make a buffer solution. And in a buffer solution, you have to consider both the weak acid and weak base. But in this case, you're going to have a strong acid or a strong base left over. And because of that, the H2O and the NaCl won't matter at all, right? H2O is neutral, NaCl is a neutral salt. So basically, all we actually care about for strong reactions are HCl and NaOH. Right? So I'm going to add these two things together, and I need to figure out how much remains afterwards. Because of that, I have to do a little bit of stoichiometry. I'm going to draw the bra table. Right? I need to put everything in moles to see how many moles of each thing I have. I cannot just directly use the molarity because the molarities are going to change as you add these two liquids together. Right? If I add 400 extra milliliters to this solution, my molarity is not 0.25 anymore. I just watered it down, and vice versa. So off to the side, I'm going to write HCl, figure out how many moles of it I have. Its molarity is 0.25 equals moles divided by liters. 500 milliliters is 0.5 liters. So 0.5 times 0.25, 0.125 moles of acid. I'm going to repeat that for my base. The base's molarity is 0.2 equals moles divided by its volume, 400 milliliters or 0.4 liters. 0.2 times 0.4 gives you 0.08 moles of base. So I have more moles of acid than I do base, so I should have some acid left over when I'm done. I'm going to take these numbers for moles and plug them in over here. 0.125 moles of HCl, 0.08 moles of NaOH, and I have none of this, but I don't care about it at all. When these two things react, they'll react until the limiting reactant's used up, which is basically the smaller number. So subtract the smaller number, and you'll have none of that left over. Subtract the smaller number also over here. 0.125 minus 0.8 is 0.045 moles of HCl left over. I'm still looking for pH, so I need to find concentration of H+. Concentration always means molarity. So I cannot use moles and directly plug it in, or it'll be wrong. So what I'm going to do is do another molarity formula. Molarity is moles, 0.045 divided by volume. And because I added two solutions together, the first one was 500 milliliters. Oops, can't see that. The second one was 400 milliliters. I'm just going to add that together to get my new total volume of 900 milliliters or 0.9 liters. 0.045 divided by 0.9. It's a nice 0.05 molar hydrochloric acid. Since I have molarity now, I can use the pH formula. This is a strong acid, so I'm just going to immediately use the regular pH formula. Negative log of 0.05. .30 is my answer. Okay. So in this question, I've mixed a strong acid and strong base together. I used some stoichiometry after I wrote my reaction to figure out what would be left over when they reacted. I had a strong acid left over. Since I have a strong acid left over, I just convert it back to molarity, plug it into the pH formula. Okay. So this is also the same thing as a titration, right? This is exactly what a titration is, right? You have an acid and you add a base to it. Titrations are just neutralization reactions. We can just do a couple like lab activities with them, right? So anytime you add an acid and base together, doesn't matter if they're strong, doesn't matter if they're both weak, you use a full right arrow neutralization reaction, write your products, convert everything to moles. We have to convert to moles anytime our volume changes in a problem, like it did in this one. Okay, plug our moles into the broad table. This is just to do stoichiometry. Subtract the smaller number because that's how much gets used up from here and used up from here. Here's how many moles I have left. You'll usually have just one thing left over. That's a strong acid or a strong base. Turn it into molarity, plug it into the pH formula. If you end up with a weak acid left over, you can't do this step. You would have to use the Henderson-Hasselbalch equation and maybe do a little bit more work. Okay, number 6. The pKa of hydrozoic acid, HN3, is 4.72. Okay, so a lot of problems start by giving you the Ka. This time it started giving you the pKa, but that's fine. If you need the Ka, you could just swap them back and forth. Maybe you'll need the pKa, but this is the same thing. Weak acid has a pKa. So this is my weak acid. It reacts with water according to this reaction, and it gives you its reaction. So it shows when you react with water, you lose an H to make NH3-. Water gains the H+ to make some hydronium ion. I want to calculate the pH of a solution formed from 100 milliliters of 0.9 of my weak acid and 50 milliliters of 0.3 molar NaOH, strong base. This water reaction is like not really that important yet, at least. Right? The most important thing is this last sentence. I want to find the pH, and I have weak acid and strong base, and I'm adding an acid and base together. So I'm actually not going to immediately use this reaction, which I think is misleading and how they're trying to trick you. I'm going to write the reaction of my weak acid reacting with my strong base. Before I can find the pH or anything, I need to see how much of this acid and base react with each other to see what I have left. So my acid, HN3, I'm going to add it to my base, NaOH. They're going to react fully to see what I have left. My acid, the H and the OH make H2O. And my base, or my other thing, Na, combines with the N3 minus to make NaN3. Now, H2O won't matter because it's a liquid. Liquids are never included in equilibrium reactions at all. But in this case, Na matters. NaN3 matters. And that's only because this is a weak acid. The conjugate base of a weak acid does affect the pH. The conjugate base of a strong acid does not. And that's the only difference, because one of these things are weak. I'm also going to take into consideration how much of this I have. Because if I have some acid, and weak base, it's a buffer, and I can find pH using the Henderson-Hasselbalch equation. So this is very similar to the last problem, except I have a weak acid instead of a strong acid. I'm going to go about solving it the exact same way. I'm going to figure out how many moles of each thing I have. I'm going to start with the NH3. Sorry. It's habit trait NH3, not this is the same thing but backwards. All right, my molarity is 0.9 equals moles. My liters is 100 milliliters, or 0.1. That's 0.09 moles of acid. Plug that into my stoichiometry broth table. NaOH, I had 0.3 molar equals moles, and I had 50 milliliters, or 0.05. 0.3 times 0.05 should be 0.015 moles base. Plug that into the broth table. I have no NaN3 to start the problem. All right, as my reaction goes, I'm going to react until one of these things runs out. This one's a smaller number, so that's the one that'll run out first. So I'm going to lose 0.015 of my NaOH and 0.015 of my NH3. Gives me 0.075 of it left. But I'm actually going to turn some of that into the conjugate base. So I end up with 0.015 of my conjugate base as well. And because all of this was in moles, I still have moles. So compared to the last problem, the difference is I have a weak acid left over. When you have a weak acid and a weak base, you can use the Henderson-Hasselbalch equation to find pH. You can now use this reaction if you want and make an ice table and fully solve and set up your Ka and do all that work, but that actually complicates it. Instead of doing all of that, our shortcut is to just use the Henderson-Hasselbalch equation. You'll get the exact same answer either way, assuming you do all the work right. But I would much prefer to just do this instead of writing all that ice table. I'm going to plug in everything except, again, I have brackets, which means I need concentration. So I have moles, I need liters. I need to use the liters to find molarity. So let's do that. Instead of showing a whole different step, I'm just going to divide the moles by my new liters. 950 is 950, or 0.95 liters. So taking this number, dividing by 0.95, I'm just going to write it over here. 0.0789 molar. This is my acid, my weak acid HA. My base, I'm going to do the same thing, divide by 0.95. 0.0158 molar conjugate base. Those are the numbers I'm going to plug into my Henderson-Hasselbalch equation. The pKa was already given to me. I don't even have to do the negative log. I'm just going to take the pKa, just write that whole number here, which is nice. Times the log of my conjugate base, 0.0158, divided by HA, 0.0789. pH equals 4.72 plus this number. Okay, when I'm looking at this, I'm seeing I have more acid. My bottom number is bigger, which means the pH should go down a little bit because I have an excess of acid. So I'm expecting my answer here to be a negative number. The log of 0.0158 divided by 0.0789, in fact, is a negative number. It is minus 0.698. So I'm going to add a negative 0.698 to my 4.72. I get 4.02 as my final pH. Right, so it's very important to identify weak and strong acids and bases when you start the problem, because that's how you're going to evaluate your problem solving. An interesting quirk of this type of problem is this step here and here actually is kind of optional. The reason being, all we care about when we do the Henderson-Hasselbalch equation is the ratio of acid and base to each other. So if you used these numbers instead of these numbers, you would have got the exact same answer, because the ratio here, 0.075 to 0.015, is the exact same as this ratio, because you divided each of them by the same number. That usually isn't the case, though, so that's why I went through the steps and did it the formal way by plugging molarity in here. But technically, if you left off that step, you would get the exact same answer. Even though these numbers are different, this number would be the same because we're looking at the log of a ratio. And that's never the case with a strong acid. If you would have done this problem without doing this step, your answer would be different. It's just a weird quirk of a buffer problem specifically, that you can plug moles in here and get the same answer. But it's more of a coincidence just based on the math. It's not something I would recommend doing. All right, number 7. What is the hydronium ion concentration? Okay, remember hydronium is H3O+, which means the exact same thing as H+. Right? Usually they'll be specific and tell you what hydronium is just to be sure, but it is important to know. They can just use the word like this without telling you what it is. You're expected to know it. Okay? So kind of how I think about it, it's hydro. So I think of water, but like neum, I don't know. It makes me think of like an ion, I guess. Hydronium ion is just like water's ion form. So it's like water with a plus, basically. Okay, so I'm looking for H plus this time. H plus and pH are usually related, so maybe I'll have to do some pH this time. It's kind of what I'm thinking in my head. Maybe not, though. Of a solution formed from 150 milliliters of 0.25 molar ammonia in H3, that is a weak base. Right, and I have my milliliters and my molarity, and 100 milliliters of 0.2 molar hydrochloric acid, that is a strong acid. The Kb for ammonia is this. So if I didn't remember that's a weak base, I could just use the fact that I have its Kb. Okay, so this time I'm mixing an acid and a base together just like last time. I've just swapped the strong and weak, but nothing's going to change. I'm going to mix these two things together and see what I have left over. So I'm going to start my reaction. I always like to write the acid first just because that's how my brain works, but if you swap it around, it doesn't actually matter. I'm going to combine my acid and base together, hydrochloric acid and my ammonia. Right? This one doesn't have an OH, right? So most bases have an OH in them, or lots of the ones we use, and that's where we just do H and OH make water. So in this one, we have a slight different reaction that happens, and it's just our normal definitions of acids and bases at this point. The acid will lose an H+, that H+ will go over here. So the H+ is gone, you're left with Cl- and NH4+. Now sometimes you might see this written as just NH4Cl. because this has a positive and negative charge. They're attracted to each other. They make a salt. So you might actually see these combining just to make that one product. It means the same thing. Okay. Either way, which of these two do we care about? Well, the Cl is the conjugate base of HCl. But since HCl is strong, I don't care about the conjugate base. Okay. I do care about NH4 plus though, because NH3 is a weak base. So its conjugate acid is at least some amount strong. Right? At least some of this will react back into NH3 plus. So that's kind of how I evaluate which product I'm going to care more about. Now, if you would have wrote this whole thing, it would be the exact same number, and you just would use this entire thing. So either way you write this, we care about either NH4 plus or NH4Cl. This is the ion form. This is the salt form. You'll have the exact same numbers. It doesn't really matter which form we choose to use. I think this form looks nicer because we'll use the Henderson-Hasselbalch equation for this one, and you can clearly see that these things are related by an H plus difference. But using this, you could use it exactly the same. You'll get the exact same number. The Cl canceling won't change anything. Okay, so this is my acid and base reaction. It's going to be a broad table. Okay. I'm going to calculate how many moles of everything I have. I'll start with HCl. I have 0.2 molar. I have 0.1 liters, meaning I have 0.02 moles of HCl. NH3, my weak base. All right, my molarity is 0.25 equals moles over 0.15 liters. 0.25 times 0.15 is 0.0375 moles. Plug that in for NH3. I have none of this to start. The only way you would have a number on the right is if the question specifically said, I also added 1 mole of this to the product. It would say explicitly, you also added some extra source of NH4 ions or something. All right, these two things will react as much as they can. This is the smaller number, so that's the one I'm going to subtract. I'll be left with none of my strong acid, and this number will go down to 0.0175. My NH4 will go up by 0.02, and I make exactly 0.02 of my conjugate acid. All right, so this time I'm left with a weak base and its conjugate acid, so I'm again left with a buffer. So I want to use the Henderson-Hasselbalch equation. But I need to be careful about which one I use. I'm looking at a weak base this time, not a weak acid. So I'm going to use the POH version of the Henderson-Hasselbalch equation. It's mostly the same, except instead of pKa, use pKb because you have a base, plus the log of, it's still going to be products over reactants. So it's still going to be NH4 plus over NH3, but how you'll usually see that written on like a formula sheet, this is BH plus. So it's the base with an extra H plus, just like this one has, versus just the base by itself. Base. It means the same thing though. It's always going to be your product over your reactant. The POH equals pKb. By a weird coincidence, ammonia is also 1 times 10 to the negative 5, just like acetic acid is. So we use this number all the time for some reason. Plus the log of my BH concentration. Wait, what did I leave off? These are concentrations. This is still just moles. Like I said, you can plug it in and get the exact same answer, but let's be thorough. Convert both of these to molarity. Okay, my new volume, when I add these two things together, I have 0.1 liters plus 0.15 liters. I have 0.25 liters. So I'm going to divide both of these by 0.25. It won't actually change my answer, but I should be thorough. 0.0175. Divide by 0.25. It's 0.07. That'll go on the bottom. 0.02 divided by 0.25. It's 0.08. That'll go on top. All right, go solve my pOH formula. The negative log of this is 4.74, just like it was last time, plus the log 0.08 over 0.07. I'm just going to do the log of 8 divided by 7 because it's the exact same ratio. Get rid of the word log there. 0.058. Add those two together. My pOH, add 4.74 to that, is like 4.8, pretty much exactly. Which could be the answer sometimes, if that's not what I'm looking for. If I go back to my question, I'm looking for H plus concentration. And this is the pOH, so we still have a little bit of weird work to do. I'm going to swap this over to pH, because the pH is related to H plus. And that's just 14 minus 4.8, which gives me, 9.2 as my pH. Which also could have been my final answer, but I want H plus concentration, not pH. So I'm going to set up the pH formula. That way I can find H plus. Plug in 9.2 is the negative log of H plus. 10 to the negative 9.2 equals H plus. Technically that's an answer, but you should probably plug it in to simplify it. And you get 6.31 times 10 to the negative 10 as your final answer there. Super fun. Whole lot of work there. These last couple steps are kind of superfluous. You never actually have to show this whole work if you don't want to. If you just kind of remember the shortcut, if you have pH and you need to go backwards, you just do 10 to the negative pH. That expression will get you H plus concentration. Or if you want to find OH minus concentration, you can do 10 to the negative pOH. That's kind of a shortcut way, and that's usually how I would just type that in. You don't actually have to show all these steps, but you can. A few more questions. Number 8. Given the following titration curves, so here are two curves, A and B, which curve represents the titration of a weak base, and which one represents the strong base? So the easiest way to tell is just looking at like symmetry and how nice and symmetric the curve looks. If you look at A, it has this really nice uniform shape. It goes over really flat, sharply down, and then really fast down, right? That's how A looks. If something is very symmetric, that means that you have a strong acid and strong base together. Now, the second curve it gets all wiggly and weird at the beginning. It kind of goes flat and then goes sharply down, right? That's a great, perfect sketch of what B looks like. And that's because this area of B is called the buffer zone. And the pH changes weird at the buffer zone because you have a weak base mixing with its sorry, I just write B for weak base, mixing with its conjugate acid. And it makes a buffer, and buffers resist a change in pH, which makes this area pretty flat. The pH won't change very much once you have a relatively similar amount of B and BH+. So to answer this first question, all you have to do, A is the more symmetric one, so A equals the strong acid and strong base together. B is the weird one. So during B, you have a weak base and a strong acid. And I know it's this order. I know I have a weak base and a strong acid. You just look at where you start. If you start with a high pH, that means you start with a base and you're adding an acid to it. And because this weirdness is in the base part where the pH is above 7, I know the base is the weak thing. On this one, I have a strong acid because the acid part is nice and smooth. All right, for both of these, I want to estimate the pH at the equivalence point. So I'm going to do my best. They're kind of overlapping each other. So I'm going to start with A. You're going to go to the middle of this sort of curvy area, which would be about there if I had to estimate it. And the pH for A is exactly 7. By definition, it should be 7, and it does look pretty close to 7 based on my estimation. Strong acid and strong base together, the pH is exactly 7 at the equivalence point. Now the other one, because of this weird down curve area, if I'm thinking about exactly where this curve is in the middle, I'm thinking it's actually a little bit more down here for curve B, right? That's kind of more the center of that inflection point. And that pH is actually way below 7. So I'm going to do my best to kind of estimate, and I'm going to say for B, the pH is around 5.2-ish, something like that. All right. And last, what can you infer about the concentrations of the two bases? Okay, so the concentrations of my weak base and my strong base, right? Do I have the same amount of each of them? All you have to look at for this, we're using the same acid. Let's just pretend it's HCl. We're adding the same acid to them. And look, you need the exact same amount of acid to completely neutralize them, right? So that means their molarity is the same. All right, number 9, what is the pH of 0.785 molar solution of formic acid? Okay, formic acid, thinking it's a weak acid, here's its Ka. The difference between this problem and the ones we've been doing in the last couple is I don't see any base being added. All I have is a weak acid. So I just have a simple weak acid, and I want to find its pH. So this is back straight chapter 15 stuff before we've added all these extra steps that can make it confusing. I have an acid, and I want to find its pH. It's a weak acid, so I can't use the pH formula right away. I can't just plug my H into here because this is a weak acid. If it was a strong acid, I'd just do this and then my problem would be done. Instead, I'm going to write my ice table. Right? I don't have to do stoichiometry because I don't have an acid and base being added together. I'm just going to set up my ice table here. It's going to lose an H+. I'm going to be left with my formate ion there. My ice table, my initial amounts of everything is 0, or sorry, not 0, 0.785, 0, and 0. My reaction has to proceed to the right because that's where my zeros are. So minus x plus x plus x, 0.785 minus x. X and x are my equilibrium concentrations. All right. So now if I solve for x, I'll know how much H plus I have. That's the number I'm going to plug in here. So I need to find x, and then I'll plug it into the pH formula. To do that, I need my Ka. My Ka is my products over reactants. So I have product over reactant. Just plug in your equilibrium values to your Ka. Your Ka was given to you, 1.77 times 10 to the minus 4 equals x times x is x squared. 0.75 minus x. Here's where we're going to go ahead and get rid of that minus x term to simplify our math. I'm going to multiply this up here. And I get 0.000139 equals x squared. Okay, take the square root of it. Square root of that answer. It's 0.118 equals x. Okay. That's going to be plugged in for H plus because x is just H plus. That's where I plug into the pH formula. pH equals the negative log of that answer. .93. Final answer. Last problem for today, number 10. The Kb for methylamine, okay, Kb, and here's the formula. I know it has to be a weak base. And it gives me its Kb. What is the pH of 0.25 molar solution of methylamine? Right, so this time I just have a base. I don't have any acids or anything. And I want to know its pH. So since it's a weak base, I can't immediately use the POH formula. I have to write out my formula. So here's my weak base. When it reacts, it's going to gain an H plus, but where does it gain an H plus from? Right, well, that's kind of where we have this invisible water that we can use. So anytime you're doing a base equilibrium, it might be helpful to kind of off to the side think about water is going to be our acid in the situation. This will be dissolved in water because all acids and bases are dissolved in water, right? So that's going to be our H plus source, and that's where the extra H is going to come from here. CH3NH3 plus. I added the H here because that's kind of, I know what the compound would be, but if you added the H over here, it'd be fine too. Okay, so that is my compound. And the H is left, when I take an H plus away from H2O, I'm left with the OH minus. Right, my ice table here. I can ignore the H2O in the ice table because it's a liquid. My initial concentration of my base is 0.25. My initial concentrations of these things are 0. That's a 0. Minus x plus x plus x. 0.250 minus x, x, and x are my equilibrium concentrations. I'm going to write my Kb expression, B, because it's a base, x times x over 0.25. Just going to get rid of the minus x. My Kb, I'm going to plug that in, is 4.47 times 10 to the minus 4. I'm just going to write it over here instead. Multiply 0.25 up. 0.25 times 4.47 times 10 to the minus 4th gives me x squared equals 0.00011118. Square root of that. X is 0.0106. Okay. X tells me OH minus concentration. So this is the same as my concentration of OH minus. A very common mistake on this problem. It's exactly like the last one, except I don't immediately know H plus, and I'm looking for pH. So I can't immediately plug this into a formula to find pH. You have to be sure to use the POH formula. Okay, so my POH of the negative log of OH minus, POH equals the negative log of 0.0106. Negative log of my answer, 1.98. My POH. So I'm just going to do my last step. pH is just 14 minus that, which is 12.02. That's my final answer. My pH is above 7 because I have a base. Okay, I hope you found that helpful in some way to kind of break down some of those problems. I would say that at least a couple of those, either word for word exactly or very close to it, will show up on your chapter 15-16 test. So I will see you for that. Have a great rest of your day.